Welcome to another edition of Coonrod's Corner, brought to you by the Rogers Corporation. Today's topic, what RF engineers need to know about PCB fabrication for optimal results. Now here's your host, John Coonrod.
Hello, my name is John Coonrod with Rogers Corporation. I am a technical marketing manager, and today I'm going to be talking about how printed circuit boards are made, and also trying to look at some of the theory taught in academia and how that applies in the real world for the industry that we work in. Now, the academia does a very good job teaching the theory. However, the theory for electrical engineering and electromagnetics, the topics are just so big and vast that they really do not have the opportunity to spend a lot of time on the practical implementation of a lot of these subjects. So I'm really going to be talking about that a lot today. And for more information, I would like to refer you to our Rogers Technology Support Hub. And at the end of this video, you will get a URL that will give you a link to that website. And there you can find much more information on the topic I'm presenting today, as well as many other topics. The graphics shown here and the following graphics is going to be a very simplified process of how to build a 2 copper layer circuit. And you start with using a copper clad laminate, which is shown here, and you have essentially the laminate is a sandwich of copper, dielectric, and copper. And the first thing you do is go through a chemical cleaning process, and then after that a photoresist is applied. The photoresist is, as the name implies, it's photosensitive, and it also is resistant to chemical attack such as copper etchant. And then after that, a artwork is applied, and the artwork is basically black areas and clear areas of a clear mylar, and the clear areas are the circuit image that you want on the circuit board itself. Shown here is a continuation of the last graphic, and now the artwork is pressed tight by a vacuum process to the photoresist, and then the photoresist is exposed by light, and whatever areas of the artwork is clear, that light will polymerize and cross-link the photoresist, and whatever is protected from the light will not be polymerized. And when the panel goes through the photoresist developer, then whatever has been polymerized will stay and everything else will be washed away, as shown in the bottom picture. Now, continuing the process, what we have now is your circuit image is now etched into the circuit board itself. However, you still have the photoresist there, and that needs to be removed. So you go through a photoresist stripping process, and that removes it, and now you have a very simple 2 copper layer circuit. In this graphic, I'm showing a cross-sectional view of a simple 2 copper layer circuit, and as a RF structure, that could be a microstrip, and a microstrip has a signal conductor on top, ground plane on the bottom. Also showing a 3D view of that. In this graphic, I'm trying to show the relationship between the cross-sectional view on the upper right, and then the circuits that actually came from on the bottom. And what this is, there are 12 by 18 panels, and it's actually the same panel, just taking a picture on top, flipped over, taken on the bottom, and you can see how the signal plane is related to the top plane of the panel, and also the ground plane related to the bottom. The evaluation panel shown here, after we have the circuits made, then we will cut them out, and in this case they're simple microstrip transmission lines. They do have grounded coplanar waveguide at the launch, and I'm showing a connector, in-launch connector, that is connected to the circuit, and then cables are connected, and then you are ready to test the circuit on your network analyzer. That was a quick overview of how a 2 copper layer circuit can be made. Now, most of the circuits in the industry today are multi-layer circuits, and this 2 copper layer circuit could be part of the multi-layer circuit, where it would be copper layer 1 and 2, and the other layers below that could be layers for power planes, ground planes, control circuits, or whatever is necessary. Now, to build a more complicated circuit like a 3-layer circuit or a 4-layer or more, you do need some connection between the different copper planes, and that's where plated through-hole technology comes in. So the next several graphics, I'm going to show how to build a simple 3-layer circuit and also talk about some of these electrical vias. Shown here is the starting process of building a 3-layer circuit. In this case, what we did was we started off with the 2-layer circuit we built previously, and that is going to be the bottom copper layer 3, and then the middle copper layer, which will be copper layer 2. And that middle layer is the signal layer, and it's going to be buried in this case. And what's going on top of that are layers of prepreg. Prepreg is a bonding material, and it will laminate and glue together the various materials. And above that will be a raw copper foil. The copper foil is a lot like aluminum foil, except it's copper and it's very thin. So then you go through a process of lamination to laminate all these together, and then you have a 3-layer circuit. Shown here is a continuation of the process to build a 3-layer circuit, and this is after lamination where we pick up. And you can see the signal layer is in the middle, and it does not have access to the outside world. So if you need to connect to the signal layer, which you will, you need to somehow connect to it, and that's normally done by plated through-hole technology. So the next step is to drill holes through the circuit in areas that you want good connections, and then after that, the copper plating will be done to plate copper on the surfaces and through the holes. Essentially, everything is connected together at this point in the bottom right picture. It's all connected together with this copper plating. Continuing the process, now we have fabrication that needs to be done on the outer layers, because if not, everything is all connected together by this copper plating. So now what you do is just go through the same process that we did initially to build the 2-layer circuit, where you put photoresist on the outer layers, expose the circuitry on the outer layers, and etch away the copper that you do not want. And now you have the signal conductor that is buried, that is attached to this via and can be connected to the outside world. And also the ground planes, top and bottom, are connected together as well. This graphic is essentially the same graphic as the last one, except I wanted to put in there a 3D view so you can get a sense of how this circuit can now be connected. So if you have a vertical connector that you put down onto this circuit, the ground shroud of the connector would make contact with the ground plane of the circuit, and then the center pin of the connector would make contact with that via there that goes down to the middle of the circuit, and then the energy would be on the signal plane where you want it. Now I want to discuss some of the different techniques that can be used to connect different copper layers together. And these are vias that are plated with copper to make the electrical connection. Now this looks like a more complex circuit than what we talked about so far, and it is, but actually you already have all the information you need to be able to build this. And first off, what you do is you'd start with building copper layer 2 and copper layer 3 by just a copper clad laminate. And essentially starting off as we did to make the 2-layer circuit. But first we'd start by drilling a hole and then plating copper everywhere. Then we would put the photoresist on top and bottom and then expose the circuitry and etch it. And that's how you get copper layer 2 and 3. Then top and bottom of that, the dark gray, that would be the bonding material. You'd put layers of bonding material, prepreg in there, and then you put copper foil top and bottom of that, laminate it together, then drill the holes on the left and the right all the way through the circuit, and then you have a laser come in and it will burn a hole from the top layer down to the layer below it and reflect off it on the top side and the bottom side, and that's making the microvias. Now after that, you put photoresist on top and bottom, again goes through the same process as a 2-layer circuit. Photoresist, put on your circuit image, etch what you don't want, and there you have a 4-layer circuit with multiple different kinds of vias. The point of this video is to help the RF engineer picture and understand how a circuit is built. There are several different types of technologies that can build a 2-layer circuit, 3-layer, or multi-layer circuit. I've just given an example of some simple processes to do that. Now, the RF engineer should really contact their PCB fabricator and talk to them about their particular build and try to understand the different variables, because in making a circuit there is normal fabrication variables that do change from circuit to circuit, and understanding that and having RF simulations and models to account for that is very important. Shown here is a list of information, and I'm not going to go through this in any detail, but since this is a video, you can stop the video and read the different bullet points. I will make a point of a few things that need to be talked about. One is the trapezoidal effects that is mentioned in the notes. What that refers to is the microstrip circuit shown to the right on the top circuit and the second circuit just below that. The top circuit is showing a microstrip circuit with rectangular conductors, which is normally what software will assume, and that's ideal. However, if you take a microsection, a cross-sectional look of circuits as they're built, what you normally see is the second picture down of the microstrip, and the conductors are not rectangular, they're more trapezoidal shaped. And that trapezoidal shape does vary from one circuit to another. Now in the case of microstrip, that trapezoidal shape does not change the RF performance much, very little. In the case of grounded coplanar waveguide, the trapezoidal shape can change the RF performance significantly, especially at millimeter wave frequencies. Now, grounded coplanar waveguide, that's the third picture down and the one at the bottom. And the difference between those two pictures is showing copper thickness difference. And the third picture down is a grounded coplanar waveguide with thin copper. The last picture at the bottom is the exact same design except with thick copper. And I'm showing electric fields in blue, and you can see that the thicker copper has much more electric fields in air, and air is a low dielectric constant, so that means that circuit will have a lower effective dielectric constant than the third circuit that has thinner copper. In summary, I've shown how to build a two-layer circuit, a relatively simple one, a three-layer circuit, and even a four-layer circuit. I've also shown how you can get connections between the different layers by using plated through-hole technology. This concludes this session of Coonrod's Corner. Thank you for watching.
For additional information and technical tools, if you're not already a member, join the Rogers Technical Support Hub and gain access to calculators, technical papers, and more Rogers Corporation informational videos. Rogers Technical Information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.